Welcome. Today is the second part of the conservation of energy lecture. In the first, I talked about all the different kinds of energy and what the formulas were. In this one, I'd like to go into a little bit more detail about springs and specifically Hooke's law, and then talk about how to actually solve conservation of energy problems. Okay, so we'll start with springs. So now that you've done the spring lab, I'd like to talk a little bit about Hooke's law. Okay, so Hooke's law is actually the equation F equals kx. Remember, a law is not a theory that's all grown up. A theory is not a hypothesis in science. It's an explanation with a lot of evidence behind it. A law is an explanation that's simple enough to write in an equation, right? So that's why this is Hooke's law. And again, like several other laws, it's not always true. It's true for springs if you don't overstretch them. Okay. All right. So first of all, let's talk about the variables. So F is force measured in newtons. K is the spring constant. Now, warning, this is one of a couple places in the reference tables where they use the same letter for two things. Lowercase k is both the spring constant, it's also the electrostatic constant that's listed on the front of your reference tables. That's not this, okay? The electrostatic constant is true everywhere in the universe. The spring constant is different for every spring, right? So if you think of a spring that's really hard to stretch, like a hand exerciser, that would have a high K, and a spring that's really easy to stretch, like a soft rubber band, would have a low K, okay? And then X is the change in spring length, okay? So if you look at this little picture here, right, we put one weight on it, it's changed the spring length X amount, and we put twice that amount, it's changed the spring length twice that amount. Hopefully, when you did your lab, you got a graph that looked a lot like this. So X, again, is that change in spring length. Here, they're representing it as displacement. All right, also measured in meters is basically another word for the same thing. Okay. The other thing I want to warn you about is that this is the one force all year that's not a constant force, right? Usually we've been dealing with constant forces, which produce constant accelerations. In fact, all of our motion formulas depend on constant forces and constant accelerations. If you don't have constant forces and constant accelerations, you need calculus to deal. Now, we don't need calculus here. I just want to point out that this is not a constant force. The more you stretch the spring, the harder it is to stretch. Okay, and then somewhere out here, you overstretch the spring and it becomes warped and it never looks the same way again. Okay, this force is an instantaneous force, okay, or like the force at any instant. So for example, in this graph here, okay, if I stretch the spring 0.06 meters, then it will produce a force of around 12 newtons, okay? And if I stretch it 0.1 meters, it will produce a stretch of 20 newtons, or you will need 20 newtons of force to do that stretch. Yeah, I said it kind of wrong the first time. Now, this means you've got to be a little bit careful about that word average or constant force if you see it in a problem. It means you cannot use this formula unless you kind of like do some fancy gymnastics where you're like, well, if the average force is here, then the total force will be up here. But that's not the easiest way to do it. If they use the word average force, okay, in a spring problem, it is easiest to approach that spring problem from a work perspective, all right, how much the force times the distance is, and not use Hooke's law. Do not put constant forces into, or average forces, if they use these words, into this formula. They will not work, okay? Fun fact, also, if you've ever wondered where the 1/2 in the PE, so if you remember PE equals potential energy of a spring is 1/2 kx squared. If you're wondering where the half comes from, remember how areas and slopes have meaning, right? The slope of this graph actually means the spring constant. Just make sure that you always put the force on the y-axis. And the area under this graph is actually the energy. And since the graph is a triangle, that's where the 1/2 comes from. When you come back here, right? All right, so that's just to kind of fill in that information. Now, we're going to kind of change tactics here. So yesterday we looked at different kinds of energy diagrams when there was conservation of energy, meaning you're in a closed system and we're not going to do any external forces. We're not going to do any work. There's no friction. You're going to use this idea that the initial energy is equal to the final energy. But in the working world, work changes the amount of energy in a system. Let's look at an example. Okay. Now, again, we have these little energy bar diagrams, which at this point you should have played around with in the little activity. Okay, we got a skier coming down. On when he's on the slick snow, there's no friction, and then at the end here, he hits the unpacked snow. And notice this is work due to friction. Okay, it's below the axis because the work is actually taking energy out of the system. All right, so again, he starts with PE. He ends up with that PE is slowly turning into KE. He's at his maximum speed way down here, and then he hits the unpacked snow, and it starts to take the total mechanical energy out of the system. All right, and by the time you're at the end, it's all gone. All right, okay. I would like to show you how this works with, whoops, let's go back here. One more slide here, and that is this guy. Okay, so when you're solving conservation of energy problems, I want you to think of a couple of things. I can't get to the right slide. I suck. Okay, I want you to think of it in terms of work and energy lost equals work and energy gained. Okay, because most problems are simple enough to think about this, right? So if it starts at the top, all right, and then it comes down a hill. All right, so this is kind of like what the skier was doing on their way down. You can think of this as the PE lost equals the KE gained, meaning if he had 10 joules of PE at the top of the hill, and then he loses all that PE, then he's going to gain 10 joules of kinetic energy. Okay, what if there's work done? All right, so for example, let's say you're pushing something and giving it speed, right? So you're applying a force for a certain amount of distance, that's work done, and then you're causing something to gain speed, all right? So the work that you do in pushing that object will equal the KE gain. So for example, if you did 10 joules of work pushing the object, it would gain 10 joules of kinetic energy, all right? You could also think of this kind of like at the end of that skier, right? So all the KE that he had gained, all right, now turns into work due to friction. So once again, if you had gained 10 joules of kinetic energy, all right, at the bottom of the hill, actually this should be a loss, not a gain. But if you lost KE, 10 joules of KE at the bottom, then he would gain that would be used for 10 joules of work. All right, and then finally, you could have a more complicated thing where maybe you both have PE and KE. So like, let's say you're at the top of a hill and someone gives you a push, okay? All right, as you go down that hill, the PE lost and the KE lost will turn into the KE gained. Okay, so that's kind of a really complicated example. As you're doing the problems on the test wizard, use these ideas and notice they're always a little bit different. You have to kind of think about those energy bar diagrams and what kind of energy is it losing and what kind of energy is it gaining. All right, good luck with that. Okay, yes, have a wonderful day.